Welcome back to part 2 of week 7, where we're still talking about fission, fusion, and radioactive decay. When we kind of left off, and here we're starting with conservation laws. So we still have this idea that matter is neither created or destroyed, so we know that law of conservation of matter, stream of energy. Okay, so we've learned that previously. They apply to chemical reactions, but they don't really as much apply to nuclear. Because mass can turn into energy, so we kind of have this difference. So we have two other laws that apply to nuclear reactions, okay? The law of conservation of charge says that the charge of the reactants and the charge of the products must be the same. Then we have the law of conservation of nucleon number, saying that the total number of nucleons must be the same before and after the reaction. And a nucleon we kind of give as a proton or a neutron, so that meaning that total number of protons and neutrons must not change in the reaction. Okay? So in chemical reactions, are charge and nucleon number conserved? Then yes, they are. Okay, they are conserved. Now, we can check this, and I think I talked to you a little bit about this in the last video, in the sense of you're looking at the numbers, and so you want the numbers to equal on the same side. So 235 here right on the left side of the arrow. If you add 4 plus the 231, you get 235. So you're conserving the same number on both sides of this arrow. Same thing with 92. If you add 2 plus the 90, you get 92. So that's just kind of looking to making sure that we're keeping stuff equal on both sides of the arrow. Okay, for the reaction. So if I look down here, you kind of look and see, okay, which one has added, 4 plus 229, that doesn't add up to 231. I think it's B, okay? If you look at both of those numbers, the 2 plus the 89, 90, it should be correct, okay? And that's just what you do, just making sure that our numbers stay the same. It's very important. Okay, so let's go back to some of the dangers and uses of all of these different types of decay. So alpha particles can be very dangerous, okay? They're large, okay? They're made of 2 protons and 2 neutrons, which may not seem very big, but it's big enough to cause, it to be quite dangerous. So they're big enough that they don't penetrate the skin, so they don't go through your skin, but if ingested, they can cause the atoms they hit to come apart into pieces. So that's kind of the problem. So they say exposure to this alpha decay can be up to 20 times more damaging to the atoms than other types of radiation. Okay, but they can also save lives. So we have different detector particles that are in a smoke detector that can identify things going on, and so that is kind of sounding the alarm. They see the air gap and it can recognize this. It's safe life. So we do use this as well for positive things. So again, we're viewing alpha decay. Well, the symbol for alpha decay looks kind of like an A. It's right up there. It's the Greek symbol for alpha, and it says well. So to review alpha decay again, what type of particles are made from the nucleus? Okay, remember it's the 2 protons, 2 neutrons, which is a single helium, a nucleus. So it's an alpha is helium. Okay, and then what's true about it? It is very damaging because they're so large. Okay, that's the reason they are damaging, is because they are large. It can be harmful to us as humans. Okay, so again, we're looking at beta decay. To review this a little bit. So one of the neutrons in beta decay turns into 2 particles, a proton and an electron. So it kind of takes one of the neutrons that's there, and it releases a beta particle, and it's shown kind of what's in through this visual. It takes a neutron, and it literally makes a new proton and an electron. Okay, kind of spits out that electron is released as a beta particle, so the electron is the only thing that kind of comes out, but the new proton stays in here. Okay, so again, it's going to take that neutron, going to split it into a new proton, a new electron, and that electron is kind of released as a beta particle. Okay, so that's a beta decay, so different from the last one. We're going to still kind of write them similarly, but instead of writing helium right here with the 4 and the 2, we're going to have an electron, E, okay, because that's the only thing that comes out, and it's 0. There's no mass difference. I'm in a negative 1 because electrons are negative 1 charge, so it's going to add a proton. Okay, so 91 minus 1 is 90. Okay, so now we're going to see this negative 1 over here. Nothing happens with the mass. It all stays the same, the mass number. Okay, and that's because the neutron just changes the proton, which is still affected in the mass, so it's fine. There's nothing that changes. Okay, now which is the correct one that has happened. Okay, so if we look at everything, the negative 1, 7 is okay, 6, but that changed. 14, 15, that stayed the same, but that didn't change. Okay, so I'm looking at, I think D is the right answer. Okay, so there's dangers and uses. Okay, so beta particles can cause cancer, but they can also be used to diagnose or cure cancer. So pluses and minuses. Okay, they're smaller than alpha particles. It's just an electron, and so they can quickly travel to many cells and damage them. Okay, because we know alpha particle can hit one cell and cause great damage to that one cell, but they can travel to many cells and damage them. But they don't actually kill a cell, but they harm the DNA inside it, and this causes the harmed cell to produce more cells that don't function properly, which can cause cancer. But on the other hand, if we control them properly, we can then use them to diagnose cancer, and so they can do it in a scan, and we also use these in radiation therapy for cancer as well. So controlling these particles and doing different things with them can help identify cancer, but also treat that as well. So you have the pluses and minuses with beta particles. Okay, so we have this different thing going on with the true of either alpha decay or beta decay, and then what is true of both alpha decay and beta decay. So let's try to organize them all. In a sense. So what is the one that only emits a helium nucleus is just alpha. When it's just an electron, it's beta. Okay, they both obey the laws of the conservation. When we talk about a parent atom and the mass changing, it's only alpha. A neutron turns into a proton, that's beta. Okay. It increases the atomic number by 1. Remember we said that's adding a proton over here. We're decreasing the atomic number by 2. We've got alpha. Okay. Now it causes an element to transmutate, meaning change. Well, both of them kind of have them change. And releases radiation is for both of them as well. They both release radiation. Okay. Let's move on to the last few slides. So the last type, remember we had alpha, we had beta, and this is gamma radiation was the other type of radiation. Gamma, though, doesn't send off a proton, neutron, electron. It sends off electromagnetic waves and high energy, very high energy. So when we look at this, helium-3 is going to go through this gamma decay, and it's just sending off these waves. So the kind of question is, does it cause transmutation? Well, not really. It's not. The nucleus is not changing. It's still going to have the 2 protons per neutron. It's just sending off that electromagnetic wave. Now with this, it can be harmful or helpful, like any of the radiation types we've talked about. It does not cause transmutation because no particles are ejected, but they can damage living cells, and they can even cause cancer again. They can kill dangerous bacterium, so we often use it to sterilize medical supplies. So that's important, and sometimes we use it as radiation therapy for cancer as well. So, and we can also use it to trace chemicals in the environment, such as oil or gas leaks. So, could be helpful. But then again, as with anything, it has some cons as well. So the last little bit on here, we'll kind of review what's going on. So this kind of lists out the different types of radiation, and you have to try to figure out which one it is just by looking at the equation. Now, the first one here, we gotta notice the numbers. Focus on the numbers, and that'll tell you which type it is. Okay, so stays the same, Which is the only one that doesn't change the element? It's gamma. The numbers stay the same. It's still the same element. It's gamma. Okay. This one we look here, and we have, okay, 66, that's the same, the mass number, but 29 is adding 1, which is the only one we talk about adding a proton, that's beta. Okay? This one, ooh, we've got a 4 minus 4 minus 2. That's a helium. Oh, that's alpha. When we have a difference of 4 and a difference of 2 on the bottom, it's alpha. Okay, so it really just all becomes of just looking at the equation and what's happening. Okay, so 28, 28, ooh, the same. You're adding a proton, it's beta again. Okay, so that's kind of all. You just look at the differences. They're not too different, or they're not too hard to differentiate. Okay, but last but not least, so we can also calculate how much energy is produced in nuclear explosions, okay, and it depends on the amount of mass. So how much of that element you can have depends on how much energy is sent out or released. So generally radioactive decay leads to a small amount of high energy particles, but in the case of uranium, large amounts of uranium are available, and it's a very large atom so that it can produce a great deal of energy, okay, uranium bomb. So the isotope is 235 that is used in the first nuclear bomb, and so we do use that. And it goes through alpha decay, meaning it's releasing a helium. In the first stage, it goes to thorium. Okay, so if one atom of uranium decayed, just one single atom, which is a very small amount, and released that much joules of energy, how much would we produce if 1 mole of the atoms are decayed? Okay. And we have 1 mole, remember, is 6.02 times 10 to the 23rd atoms. Remember that number from a long time ago. But what you do is you multiply these two numbers together. And when we multiply those two numbers together, we should get 5.4, and I'll show you right here. Remember, to multiply scientific notation, you multiply the coefficients. And then you kind of add the numbers and get 12, because you think you had to move the decimal at the end. But anyhow, that is how much energy, which times 10 to the 12 is a whole lot of energy, that is released just with 1 mole of the uranium. Okay, so that kind of covers fission, fusion, and radioactive decay. So, good luck on the quiz, and if you have questions, please ask.